Alright, here's the last installment of the review packet, numbers 81 through 100. So the second fundamental theorem, when I presented to them the two parts of the fundamental theorem to you in notes, I think I called this one the first and the other one the second, because this is the one that you kind of end up with first when you derive the whole thing. I'm also not a huge fan of the use of the star here. This is just like times, right? Anyway, that's the fundamental theorem. The other part, if you take the derivative of an integral, those two operations cancel each other out. That's basically the gist of it. So these cancel out, and that x cubed just drops in place. So that's like x cubed squared, that's x to the sixth plus 1. The only catch is if the thing that you're plugging in there is not just a plain old x. We're taking a derivative, so you have to multiply by the derivative of what's inside. And this is the what's inside. So you can make a little circle around it, then it really looks like a what's inside. So there's that. Here, same deal, but now I have something that's not just a number down here, so I have to do x cubed plus 2, that's dropping that in there, times the derivative of what's inside, minus this. When it's just a number, you're taking a derivative, so that just goes away. But if it's got some kind of x thing like that, then we have to drop that in. So it's going to be 2x plus 2. That's dropping in there, times the derivative of what's inside. And here, we're going to find f prime of 2 if f of x is equal to this. So I'll just find the derivative first. F prime is equal to, same game, I'm going to drop that in there. That's x to the sixth times the derivative of what's inside. And so that's 2x to the seventh. And then f prime of 2 is going to be 2 times 2 to the 7th, that's 2 to the 8th, and everybody knows that's equal to 256. All right. We saw lots of examples of this kind of situation where you have a function that's defined by an integral. So the first thing you want to recognize when you see this situation is if g of x equals this integral, then g prime of x is equal to f of x. That's just taking the derivative of both sides of that equation. So here, this is a graph of f of x, but it's also a graph of g prime of x, because those are equal to each other. And probably it's going to be more useful to me to think about it as that graph of g prime. So fill in this table, and then we're going to make a graph of g of x. Okay, so this is a graph of g prime, so the easiest thing to fill in would be these, right? So that's 0, right? And then negative 2, looks like it's 1, 2, 3, and then it heads down 0 and negative 3. Right? Because this is the graph of g prime, so I'm just reading the points right out of there. G double prime, well, the second derivative of g, this is the first derivative, this would be the slope of that. So from at negative 4, I would say here, like, we don't have anything on the other side of that, so I think I could just take the slope to be that 1/2. We could debate because it really depends on how you define the domain of this function. The problem is that there isn't anything on the other side of negative 4, but we're not going to fuss about that. We'll say that it's 1/2 there. And then it's 1/2 here, and then at 0 it's 1/2, and at 2 there's a sharp corner, so the slope does not exist. And then it looks like it's negative 3, and same deal at the end. I'm going to say it's negative 3 there because that's the end point of, I'm going to pretend the domain is only from negative 4 to 4, and then I only have to look in that direction. All right, so what is the g function equal to? Well, g of whatever is plug that thing in here and find the area. So if I do g of negative 4, that's doing the area from 0 to -4. Notice that is the wrong direction. So even though this area is above, that's going to flip the sign of it. And this area, it's a 4 by 2 triangle. So that's going to be an area of 1/2 base times height is 4, but it's negative. Right, that's this area, but negative. And just double check that that's right. 2, 4, so the area, yeah, that's right. Okay, and then -2, same thing, except it looks like I have an area of 3. And I'm going the wrong direction again. At 0, the area from 0 to 0, you haven't gone anywhere. So that area is 0. And at 2, we're now going the right direction for area. So however you do that, you're going to get an area of 5. You could do, like, just count the blocks in this case, or you can do a trapezoid, whatever. And then the area from 0 to 3 is going to be 7.5. That's what I'm seeing. It's that 5 plus this. Yep, that's right, I think. Or is it 6.5? I think it's 6.5. I'm just like counting blocks here. Imagining that piece I could take and put here, and then that's half a block, so whatever I had there plus another block and a half. Yeah, 6.5. You could do a trapezoid plus a triangle. You could do a rectangle, it's actually a square, with a triangle on top and then another triangle on the side. There's lots of ways you can geometry your way through that. And then finally, the area up to 4. This negative triangle and this one positive, same thing, would cancel each other out, and I just get this again, so it's back to 5. All right. So, well, I've got a bunch of points here, so if I want to make a graph of g of x, then I've got -4, -4, -2, -3. Just going off the chart a little bit, off the grid, literally. 0, 0, 2, 1, 2, 3, 4, 5, and then up to 6.5, and back to 5 again. So this, a piece of a parabola, which makes sense because the antiderivative of a straight line, which is x to the first, which would be an x squared, which is a parabola, and then another straight line, and like that, something like that. All right, 85. The graph of the function g shown to the right consists of 3 line segments. Let h be defined as h is equal to this, so that means h prime is equal to g. It's taking the derivative of both sides. So I'm going to write that in there. Probably going to be better for me to think of this graph as the graph of h prime. So same game here. What's h of 6? H of 6 is equal to, this is the rule for the function, it's the integral from 0 to 6 with the g function. I could write g of x dx now since I'm not using the t there. Or you could use t, does not matter. Doesn't change anything, so we need to find the area from 0 to 6. So that's a triangle that has a base of 6 and a height of 3. Well, that's going to be 9. 1/2 base times height. H prime of 6 is the same thing as g of 6, and g of 6 is 0. H double prime of 6 is the same as g prime of 6, which is the slope at 6, which looks like it is -1. There's those. For what values of x is h increasing? Well, h is increasing when h prime is positive, and h prime is positive all through here. 0 to 6, because h prime is positive. I'm really sorry if you pick this as your answer, you put this, but if you put that it's from here to here, that is the sucker answer that is never going to be right. Nobody's ever going to ask you, where is it increasing? And like, oh, here's where it's increasing. No, not going to happen. For what values of x in the open interval 0 to 12 is h concave down? H is concave down when h prime is negative, which is the same as g prime is negative, and that means the slope of this is negative. So the slope of this is negative from 3 to 8. The interval from 3 to 8. And then I want to sketch a graph of h. All right, well, at 0, when I plug 0 into the h function, I have the area from 0 to 0. So that starts at 0. And then increasing up to this point. And since this is a straight line, I know the antiderivative of that is a parabola. And now I'm still increasing. That's going to be a maximum where I go from, derivative goes from positive to negative. And I continue to here. This is all one straight line, so that's all one piece of the same parabola from here to here. And then here, this is a straight line. That's corresponds to a line with that slope of -2. So something like this. All the transitions are smooth because we have a derivative everywhere. Right? That might have a sharp corner there, but that just means it's switching from one function to the other. The derivative does exist. It's 3. So the slope of this is like 3 when it goes from one function and transitions into the next. You can read through this stuff if you want for review. The one thing that's missing in this little review section here about volumes is what happens if you rotate around a line that's not the x-axis or the y-axis. You have to put that little shift in there in both parts of it, if there are two parts. So you can look at some of our problems. We did not skip that, but they are skipped in this review packet. So we want to find a value of x that divides the area bounded by the x-axis and this function into two sectors of equal area. Okay, so the area bounded by this and the x-axis, first thing I need to do is figure out what that looks like. So I'm going to factor this, x squared plus x minus 6. I'm a little suspicious of this problem. I'll tell you why in a sec. Because this has 3 zeros, so if we were to sketch it, it crosses at 0, -3, and 2, and so it's not clear to me. It divides the area bounded by the x-axis in this function. Like that's this and this. So I'm going to assume, and if you didn't assume this, or maybe you did, I don't know, that also they might have added something to this that said like in the fourth quadrant. So I'm just going to deal with that piece and then try to find the x value that divides that piece into two sectors of equal area. Also, when we're talking about area, we're only talking, when we use the word area, we're talking about positive values only. And okay, so maybe I'll do this. I'll do the second quadrant, the -3 to 0 part. Okay, so if I want to divide this into two equal areas, then first thing I need to know is what's the area? What's from -3 to 0? x cubed plus x squared minus 6x. This is going to be a little bit nasty without a calculator, I think, but I'm going to power through. At least there's a 0. Alright, so I plug in 0 and I get 0 minus, I plug in negative 3 in here, I get 81 over 4 plus 27, minus, because negative cubed is minus, minus 27 over 3 minus 27. And let's see, that is 9 minus 20, that's minus 36. 81 over 4 is 20.25, right? So I got 20.25 minus 36. And then that negative sign is going to flip these, so I'm going to get 15.75. Okay, that was fun. And then not done, because I'm going to divide that into 2 sections of equal area. So that means there's a line that goes through that area at x equals k, where this area is equal to this area. Now you could cut this in half. That's 15 over, let's see, what is that? That's 16 times 4, that's 47 over 4. Is that right? No, that's not right. 16, it's 63 over 4. So half of that is 63/8. So I want a value of k so that the integral from negative 3 to k and the integral from k to 0 are equal to each other, and they're both equal to that, right? Because that's half the area. So I need to set up that integral. I'm going to do the one that has the 0 on one side, because that's just going to be easier. So the integral from k to 0 of x cubed plus x squared minus 6x dx. I want that to be equal to 63 over 8. And I'm starting to think that this was probably a calculator problem, and I'm just trying to power through it without one. It's kind of possibly dumb. We'll see. Let you be the judge of that. Because I think I'm going to get an equation, yeah, that I can't solve without a calculator anyway. So I plug 0 in here, just like the last one. I get 0 minus k to the 4th over 4 plus k cubed over 3 minus 3k squared. And I want that to be equal to 63 over 8. There's no way I can solve that without a calculator. So probably should have been using a calculator all along. Oh well. So let's see. I'm just going to move that to the other side. So I want to graph 63 over 8 minus all this. K to the 4th over 4 plus k cubed over 3 minus 3 squared. I think that looks good. I don't know my Windows set at 0 to 10 is the thing that we're looking for between 0 and 10. I think it is. There it is. 3 and change. So I can calculate that 0. I hate playing the game with a cursor. This is in between 1, 2, 3. It's in between 3 and 4. So I'm going to type in left bound 3, right bound 4. So it looks like we're 3.259 for k. that's not right, because I should have got some negative. Oh, I'm not looking in the right place. That's a different place where the area, sorry. I should be looking somewhere between -3 and 0, right? It's got to be somewhere in between those. So I found the wrong one, so let's scratch that. Hopefully, if I didn't mess anything up, there should be another one over here. Please? No. Not crossing. Dang it. Well, that's the right idea. I'll update that on the hard copy of the answer key, but I'm not going to spin around anymore with it right now. And that's how you should approach for your response questions. We did our best here. Something went slightly wrong, and is it as obvious as the... No, I have my parentheses there, so I don't know. Not sure what happened, but not going to fix it right now. All right. 87. Set up an integral expression and use it to find the area between the x-axis and this. Okay, so x-axis and this. So I'm just going integral from pi over 4 to 5 pi over 6, the cosine function. The antiderivative of cosine is sine. 5 pi over 6. The sine of 5 pi over 6, that's the y-coordinate of this angle. That's 1/2 minus the sine of pi over 4 is square root of 2 over 2. That was easy compared to 86. All right. These are a little bit of a reminder about the cross-section areas. I don't think you're going to see that. This one we've seen. This is half a square. Half a square. Half a square. Semicircle, that happens sometimes. Squares, definitely. Rectangles, sure. It's like usually chord times like a multiple of the chord, or some given height. Sometimes given as a function or something. And equilateral triangle, you're not going to see that. So those are the ones I think you're more likely to see in my experience. Find the volume of the solid whose base is bounded by this. So I'm going to make a little sketch here of that. Y equals x squared, x equals 0, x equals 2, and y equals 4. Not enough information given here. It would need to say cross-sections taken perpendicular to the x-axis. I think probably that's what was intended in this problem. So I'm taking cross-sections perpendicular to the x-axis bound by So this is redundant, this line here. This area is completely determined by these three. So that x equals 2 is a little bit redundant, although it does help us realize that our integral is going to need to go from 0 to 2, I guess. And then a cross-section of this is how I like to do these. I pull a cross-section out. That cross-section is this minus this. This is y equals 4. Minus this is x squared. That's what one of the cross sections is, and we're building semicircles on that. So that means the radius of my semicircle is half of that. So the area pi r squared, and they're only semicircles, not full circles. That's what the setup would look like for that. There's no way you're going to be asked to do that without a calculator, so I'll leave you to try plugging that in your calculator. See if you get the right answer. Actually, no. I'm not going to leave that because we need practice doing that. So I'm going to pull the pi to the outside, and I'm going to pull an 8 on the bottom to the outside because this is 2 squared. That's a 4 on the bottom and another 2. So I've got pi over 8 on the bottom. Then I need to do math 9. Going to go from 0 to 2. And I've pulled the pi and the 8 out, so all I have left inside is 4 minus x squared, quantity squared. So 4, minus x squared, that quantity squared. And I think I have everything in there right. I'm going to go with that. College Board wants 3 decimal places. I obey. Find the volume of the solid formed by x squared, 0 to about the y-axis. Oh, here are our other lines. So let me sketch this region, and then we'll set these up. These ones I think I will just set up for you. You find them. So I got x squared, the line x equals 0. Oh, is it the same region as this? It is. It's the very same thing. So this is 4, this is 2 here, and that's my region. Okay, so we're going to rotate that around the y-axis. If you rotate around the y-axis, that's a dy problem. That shape rotated around the y-axis is not hollow. And that's going to be x equals the square root of y, if I get it in that form. So y numbers, I'm going to go from 0 to 4. And
good afternoon, Wildcats.
There's the announcements.
Orders for the 2021-2022
Square root of y
due on Friday, April 5th.
squared. So there's my pi r squared. That's the setup for that. Rotating around the x-axis, that's this way. That's going to be a dx problem. And now I'm going x values, 0 to 2.
Order forms are also available in room 114.
And now I have an outside radius. The outside radius is 4 minus the inside radius squared dx. If I rotate around the line y equals 4, that is a dx problem parallel to the x-axis, and it's not hollow. Going from 0 to 2, it's a dx problem. And we have this function, and it's being rotated around the line 4. Right? So I put my shift in there. That's my pi r squared with the shift. The line x equals 3. That's a dy problem. So I'm going to go from 0 to 4. My outside radius from this axis is just from here to here. That's just 3, right? It's always 3, that outside radius. From here to here, it's 3, 3, 3. It's flat there. And then my inside radius is the square root of y minus 3. That's my function in x equals form with the shift, the minus 3. Those are the setups for all those. And I think I'm going to, let's see. I think I might stop there and continue in another video, because this one is already almost half an hour long.